Right now, the entire internet is rushing to prepare for a computer that, well, doesn't even fully exist yet. Welcome to this explainer. Today, we're looking at the quantum threat and the massive global race for post-quantum security. Governments, tech giants, intelligence agencies, they are all treating this future technology as an absolute, immediate crisis.
So you might be wondering, why panic over a machine that isn't even built yet? The answer actually lies in the timeline of our secrets. You see, the encrypted data we are creating today is already on borrowed time. If we wait for the actual hardware to arrive, the war's already lost.
To really grasp this, we first need to look at the invisible security system protecting our digital lives.
Think about it. Most of us never actually see encryption in action, yet it's the silent protector behind literally every banking transfer you make, every private message you send, your medical records, and even those routine software updates. It's the invisible shield making modern digital life possible. It secures everything from our digital identities to highly classified government systems. It's all running right behind the scenes, upholding the trust of the entire internet. If this invisible shield fails, well, trust fails right along with it.
At the heart of this is something called public key cryptography. It acts like an incredibly complex, unbreakable lock. It allows two completely anonymous devices to connect securely without ever having to share a secret key beforehand. Imagine your phone connecting to your bank's server. One public key locks the data, but a totally different private key is needed to unlock it. For a regular classical computer to guess the intense math behind that lock, it would literally take thousands of years. By today's standards, it's pretty much impenetrable.
But that brings us to the quantum computing threat and how these machines take a completely different path.
You see, quantum computers aren't just faster or regular computers. They process information in a fundamentally different way. Think of navigating a maze. A classical computer tries one single path at a time. It hits a dead end, backs up, and tries the next one. A quantum computer, it explores multiple paths simultaneously. It evaluates all these complex variables in unison. And unfortunately for us, this unique architecture happens to be perfectly designed to shatter the math keeping modern encryption safe.
The theoretical weapon here is known as Shor's algorithm. This is the mathematical theory that explains exactly how a sufficiently powerful quantum computer could bypass our current locks, like RSA and elliptic curve cryptography. Those algorithms rely on the fact that factoring incredibly large numbers is paralyzingly hard for classical systems. But Shor's algorithm? It gives a quantum computer the ability to find the private key almost instantly. It totally bypasses the need to guess combinations one by one, rendering our traditional public key defenses essentially useless.
But here's an important detail. Not all encryption dies. While public key cryptography is highly vulnerable, symmetric encryption operates a bit differently. With symmetric systems, the exact same key is used to both lock and unlock the data. It turns out, by simply doubling the size of that key, symmetric encryption can actually be fortified. Making that key thicker and denser renders it mathematically secure, entirely blocking advanced quantum search methods, like Grover's algorithm.
So, if quantum computers can't break everything today, why the panic? That brings us to Harvest Now, Decrypt Later, the invisible present danger.
It's a terrifying timeline. Attackers are currently stealing encrypted secrets, knowing full well they can't read them right now. Instead, they are sweeping up data in massive volumes and just sitting on it, maintaining it in dark archives. They're patiently waiting for the future quantum era. Once that hardware finally arrives, they'll just flip the switch. That means if long-lived secrets, think military intelligence or core intellectual property, are stolen today, they are already on a ticking clock.
To prevent this from happening, we need post-quantum cryptography. We have to completely redesign the lock. The goal here is to create new mathematical fortresses that neither classical nor future quantum machines can break. And we aren't doing this by building physical quantum computers to defend ourselves. Instead, we're designing incredibly advanced classical math puzzles. These are algorithms that can run on your normal, everyday servers, but they're engineered from the ground up to be completely immune to quantum logic.
And that brings us to the number 3. This represents a massive milestone achieved in 2024, when the National Institute of Standards and Technology finalized its first 3 post-quantum encryption standards. Now, this wasn't an overnight thing. It followed years of intense global scrutiny. These algorithms had to survive rigorous mathematical testing and brutal state-sponsored hacking competitions. But after surviving that exhaustive gauntlet, a new digital foundation is officially ready to be built upon.
These 3 finalized standards give organizations the exact blueprints they need for a quantum-resistant internet.
FIPS 203, which is based on Kyber, handles key establishment, meaning it protects data as it travels across vulnerable public networks. Meanwhile, FIPS 204 and 205 are focused on digital signatures. They prove that a file or a sender is actually authentic and hasn't been tampered with along the way. Think of these as the brand new physical locks for the modern internet.
But having the math solved leads us to the migration bottleneck, what might be the largest infrastructure upgrade in history.
As this quote so perfectly captures, the transition isn't just a math problem anymore. It's an infrastructure, software, compliance, and operational problem. Finding and replacing every single invisible lock embedded across cloud systems, legacy hardware, and global protocols, it's a logistical nightmare. Cryptography is woven deeply into proprietary software. It's baked into corporate networks and sits inside machines deployed decades ago. Sadly, there is no magical update all button we can push here. To survive this, organizations have to follow a strict migration path. It all starts with a massive cryptographic inventory. Just discovering where these vulnerable algorithms are hiding is a monumental task. After all, you can't secure what you can't see. Only after mapping every single digital lock can organizations begin the complex system upgrades. They have to carefully swap out the old math for the newly finalized standards, and they have to do it without breaking the systems that rely on them.
Ultimately, the grand objective here is what's called crypto agility. This is the ability to swap out future locks seamlessly without having to tear down your entire digital house. Because what if researchers discover a flaw in a new post-quantum algorithm 5 years from now? Crypto agility is the failsafe. It ensures an organization can pivot to a completely different secure algorithm in a matter of days. The alternative is spending another decade rebuilding infrastructure from scratch, all while actively under attack.
So how do we get to a quantum-safe future? How do we bridge this gap?
The reality is, the immediate future involves complex hybrid systems. We're going to have to run both classical and post-quantum methods simultaneously as we gradually upgrade the internet. Think about it. If the new math happens to harbor an undiscovered flaw, the classical math is still there to provide a proven, tested layer of defense. This bridge is going to require years of extensive testing. And right now, organizations must ruthlessly prioritize their most sensitive, long-lived data, shielding it from those Harvest Now attacks immediately.
Because the quantum threat isn't just about some distant, futuristic technology. It's about the choices we make today. We have the new math. The global standards are officially set. The race to migrate our systems has already begun. The only question left is, will our invisible foundation be ready when the quantum lockpick finally turns?